Hey, welcome to this crash course. We'll start with an overview of the design process, which goes something like this. We've got a population we need to serve, say 10,000 people. Most likely, this population is going to grow over time. If we plan the system for the present-day population, it becomes obsolete soon after it's built. We need to plan for the future population. How far into the future? Usually a design period of 30 years is considered a reasonable compromise between costs and results. And this population increase can be quite significant. This graph shows the evolution of the population numbers for a 2.5 growth rate for different forecasting methods. After 30 years, the population would have more than doubled. Next, we figure out the peak design flow by taking into account how much and especially when water is used. This figure shows the daily variations in flow for a system. At night, water is not used much, and then at noon it peaks to more than double the average flow represented by the red line. We take into account the peak daily flow to make sure that there's water throughout the day. The same goes for weekly variations. Maybe Wednesday is market day. We want to make sure there's water every day of the week, not just parts of it, so we take into account the weekly peak flow. And the same goes for the months of the year. So overall, peak flows are between 3.5 and 4.5 times the average flow for most systems. There's also a decision on how much water per person, the per capita allowance, which impacts the design of the network in a profound way. Yes, it affects the peak flows, but more importantly, if you're going to provide more than 25 liters per person per day, which you should for so many reasons, then the taps have to be really close to the homes, less than 50 meters. Otherwise, you may plan for 100 liters per person per day, but people won't have the time or energy luxury to collect it. We'll see how this little graph makes just that point in another video. Then comes the where. How do you distribute the peak flow number you came up with among the nodes of your model's layout? Take this one for example. How would you allocate 26 liters per second peak flow? A bit hard to tell. You need a method. This one is a bit easier. Maybe you distribute the peak flow evenly among the nodes. With your model complete, you check first the pressure at peak hour. If it keeps a minimum pressure, the model can deliver the peak flows, and it's also protected against contamination. When pipes can't hold pressure, they empty and fill periodically, sucking in the surrounding liquids. They can soon look like this. This is why intermittent distribution is such a bad idea. After checking the pressure, other parameters like velocity or chlorine concentration can be verified. By the way, I'm using EPANET here, which is easy to learn. Check out the books in the description below should you want to learn how to use it. Next, it's time to leave the comforting computer screen that takes anything you throw at it and take a long last look at how your model sits with the real world. Do you have land permission? Will women, girls, and everybody else feel safe when collecting water? Do you have such a mix of diameters that spares are impractical? Have you tried to honor the concerns of the users? Hopefully, people had enough opportunities to participate along the design process and there are no major surprises. Finally, the project documents are put together, making sure that they comply with the local codes and regulations. This design method is based on a worst-case demand, assuming that if the system works in the busiest hour of the day, of the busiest day of the week, of the worst month of the year, for a future population, it works for all of the less demanding cases. We'll come back to this idea. In the next video, we're going to focus on understanding pressure. Thanks for watching and remember to subscribe if you don't want to miss any of the follow-up videos.